Isha, can you check the link on your phone from his Facebook invite? Make sure the video's working for you. Do you want to go up there and dance a little bit? It'll be a bit of a lag. Does it look okay?
We were just on the East Coast. Dance yeah, like,
Ready to put you away.
So then, like, after all that, we just got back.
Oh, yeah.
Yeah, so that looks good. But I think
Are you doing the video?
Yeah. So yeah, if we can keep the side clear, yeah.
Okay. There it is. Wait a minute. It's like blending in. Really blended. This is the one day you can't duck in the back of the answer questions. We made it, but no question. Actually, maybe I they like keep it. Could you bring that down? Yeah. And it's totally staying cold. Okay. Yeah. Yeah. We don't need to So, and your undergraduate advisor,
Is everyone here?
memory. A little bit. Yeah, credit where credit's due.
Is it?
And then, when we start, maybe quick, like 45 minutes, I was just gonna ask, so I'm gonna say before, and then get started.
Yeah.
Yeah, they're still welcome to come. Okay. All right, so, you want one, right one? Okay. So it's my pleasure to welcome all of you here today for Kevin's thesis defense. Kevin earned his Bachelor of Science in Meteorology at Penn State University, where he did undergraduate research with Jose Fuentes, who was, as I understand it, kind enough to point him towards Scripps for his graduate work. So we appreciate that. Kevin started his time here at Scripps excelling in his courses, and I remember being particularly impressed that just for the dynamics course, he'd practically rewritten an adiabatic parcel model and gotten it to work as part of just a term project, whereas that has taken PhDs for others. So he began also working on a detailed model that he'll tell you about. This is not the best laid out or most elegant model, and I can say that because I wrote it. So it took quite a bit of time and persistence for Kevin to figure it out. And not only did he figure it out, he got some really interesting results out of it. Kevin also was very interested in measurements from an early point in his career, and he has been one of the best students I've seen in measurements in 20 years. And so I think that ability to measure atmospheric properties will take him anywhere he wants to go. One of the most impressive things about Kevin is his uncanny ability to figure out not only how instruments work without the encumbrance of an instruction manual, but also to figure out what makes them not work and how they break. Remember one time I noticed when we were setting up for a field project, the measurements from the previous day didn't quite look right. And before I could say anything, Kevin looks at me and he goes, I know, I disassembled it, replaced the filter and rebooted, and now it's fine. And so it was already fixed before I noticed it, which is great. So it's my hat off to Kevin for persevering to get the measurements he's going to talk about today, as well as to analyze them in a way that has substantially contributed to our scientific understanding. So with that, I can say that both Greg Roberts and I have had the distinct honor of advising Kevin, and I think you will see both his talent for measurements and for modeling in his presentation today. So if I haven't embarrassed him too much, I will let him start with his sense. Oh, and the format, so we ask that you please interrupt for small clarifications during the talk, but hold most questions to the end. We'll then have a period for question and answer with the whole audience, and then we'll ask the audience to proceed down to the party while the committee continues to question Kevin, and then we'll meet you after. Anything else I've forgotten to say? Nope. Okay, go for it.
Thank you then for the introduction. So, title of my thesis is Cloud Microphysical Effects of Aerosol Particle Sources and Marine Boundary Layer Processes. I'm going to start with an overview. I'm going to begin with giving you brief motivation for what I did and some background information to help understand the results. Then I'm going to go into the results of each chapter. There's 3 chapters. Each of these are based on a publication. And then finally, I'm going to go through the conclusions. As you can see, I have many co-authors. They all helped in collecting many of the measurements I used. But what I'm going to show you today is the analysis that I did with those measurements. So I'm going to first start with a simple diagram showing how clouds form. So if we start at the bottom of this, we have aerosol and CCN from below the cloud, where CCN stands for cloud condensation nuclei. That's just a subset of the aerosol that will form cloud droplets. So if we have a parcel there with these aerosol and CCN lifted by an updraft, the saturation will increase until eventually it reaches 100% relative humidity. At that point, it will form a cloud. Water will condense onto the CCN particles. Droplets will continue to form until reaching this maximum in supersaturation. And then throughout the rest of the cloud, the supersaturation will decrease, so new droplets will not form, but the droplets that did form will continue to grow. So afterwards, there are processes that can still affect the optical properties of the cloud, such as the entrainment. Now, the optical properties are mainly a function of the cloud droplet number concentration, cloud droplet size, and the cloud depth. So we're going to talk more about those soon. Main motivation for my work was to study aerosol effects on clouds, which are important because they affect climate. The main way they affect clouds is through the aerosol indirect effects, in which there are 2 of. First states that if you increase the aerosol and CCN concentration, it will increase the cloud droplet concentration, increasing the cloud reflectivity. Now, this is shown in this figure here at the bottom, this cartoon, where we have 2 clouds. One has more droplets than the other. Now, if they have the same liquid water content, the cloud with fewer droplets are going to have bigger droplets than the cloud with more droplets. Now, this cloud here with more droplets is actually going to be more reflective than the other cloud because it has a total droplet surface area greater than this cloud. The second aerosol indirect effect is increasing the aerosol and CCN concentrations will decrease the average droplet size, increasing the lifetime of clouds. So the smaller droplets in this cloud are less likely to precipitate out than in this cloud. Now, I mainly focused on the marine boundary layer. So to understand how aerosols in the marine boundary layer affect clouds, I need to know what are the sources of aerosol in the marine boundary layer. Just because we're over the ocean doesn't mean there isn't pollution. We still have anthropogenic pollution from cargo ship plumes, which here you can see these lines of clouds are caused by these cargo ship plumes. And then even over the continent, we can have pollution or even natural aerosol advected over the ocean. And here we're actually seeing Saharan dust being infected over the North Atlantic. Now, there are also aerosol that form over the ocean or in the marine boundary layer. One of which is sea spray, as you can see coming off of this wave here. Another way particles come directly from the ocean are from bubble bursting. Now, these particles that come from these two processes are mostly organic and sea salt. And then there are two other main marine particle types. One is, or they're both derived from DMS flux from the ocean. DMS is a product of phytoplankton production. So the DMS actually can condense onto existing particles, or it can condense to form new particles. So it results in two different particle types. I'll go over this more in the last chapter. Okay, so that's the background, and now I'm going to start with results from my first chapter titled Meteorological and Aerosol Effects on Marine Cloud Microphysical Properties. The objectives of this study was to identify the microphysical properties that affect cloud reflectivity. I wanted to understand the role of meteorological variables such as the cloud base height and updraft velocity. And I wanted to test the sensitivity of the organic hygroscopicity, or the organic composition, on cloud droplet number concentration. So the parcel model that Lynn mentioned, there's a few features I just want to go over quickly. It's initialized with particle size measurements and chemical composition from below the cloud, so we always have measurements at the surface. It uses a fixed sectional approach. It can have internally or externally mixed chemical components, and it kinetically activates particles. So here I'm showing two cases, one on the top, one on the bottom, comparing the simulation to observations. These observations were collected with Twin Otter airplane. So on the y-axis we have height and altitude for both cases. First column we have temperature, which was actually measured and used as an input into the model. However, the rest were actually simulated by the parcel model. So we have liquid water content, cloud droplet number concentration, the volumetric diameter, which is the diameter if the liquid water was divided equally into all the droplets, and last, the supersaturation. And you can see here near the bottom of the cloud, we have this maximum supersaturation, like I showed in the previous diagram. So we looked at 6 cases, and I want to first start out with the chemical composition. So if you look at these pie charts, they show the chemical composition. There's actually 2 pie charts, one inside the other. The outside pie chart shows the ion mass concentration, so molecular carbon, organic matter, sulfate, nitrate, ammonium. And then the inner pie chart shows the speciated chemical composition. Some interesting things to note are these top 2. These were considered to be plume cases. This one that's pure organic, that was actually from a smoke generator. This other plume case, which is about 60% organic and the rest sulfate, is from a cargo ship plume. And then the 2 cases below it are from the same day, but it's the background measurement, so unfluted. As you can see, there's still a large fraction of organics, more typical of ambient conditions relative to these. And then the last 2 cases here were actually measured from Mount Soledad. They are from over the ocean, so there is sea salt. However, it's also polluted from LA pollution. So one way we can tell is if you just look at the concentration. The concentration of these 2 are much higher than the background. And then same with the ambient, they're also good. So they have much higher concentration in the background. And then these distributions here, so on the x-axis we have the aerosol size distribution. So those are some of the differences in the cases that we looked at. Now what we did was we used this as model input, and then we wanted to simulate the droplet distribution. So now we're looking at droplet distributions instead of aerosol distributions, where the black is the fit of the measurements and the blue is actually the simulation. And just by looking at this, the most obvious thing is the observations are much more narrow, have much more narrow distributions than the measurements. For all cases, the exception of this one case, which I'll explain in a moment. So we wanted to look at the variables that affect the size of the particles to identify what is causing the distribution to be more narrow than what's observed. So we looked at two variables. We looked at changing the cloud base height relative to our measurement height, and we looked at changing updraft velocity. So if you focus just on the solid lines here, you can see that the changing the cloud base height will affect, here on the x-axis, we have liquid water content. Changing the cloud base height, however, will not affect the cloud droplet number concentration, except it did in this one case. And the reason is because it's the measurement height was below that level of maximum supersaturation, so particles can still activate in that range in the cloud. Now, the diameter, the volumetric mean diameter, did change because we changed the liquid water content, but we didn't change the number of droplets. So looking at the other variable, the updraft velocity, it's the opposite. We didn't change the liquid water content, but increasing the updraft velocity will increase the cooling rate, which increases the supersaturation. So more aerosols will activate to form cloud droplets. So if we have more cloud droplets, same amount of liquid water, those particles are going to be, or the droplets are going to be smaller or increased droplet concentration. So the idea was to actually use the measured distribution of cloud droplet or cloud base height and the distribution of updraft velocity and do a weighted ensemble to see if that makes the simulation more representative of what was observed for the droplet distribution. So we tried that. It's not perfect, but for example, this plume case, we're going to I'm going to show you in a minute that this case was very sensitive to its chemical composition, the fact that it was purely organic. This plume and background case are much better. We did underestimate the liquid water content slightly in this case. Now I do want to point out this ambient polluted case. If you remember from 2 slides ago, the simulation was actually better than it is now. So this is the only case that got worse. Now this case was also the case that was affected by cloud base height, where it affected the cloud droplet number concentration. Now the reason we think that this case didn't actually get better, it got worse, is because the measurement height is actually really close to the cloud base. So it's not representative of a distribution of cloud base heights and updraft velocity. For the rest of these cases were measured much higher in the cloud, so it's actually the cloud has been mixed through turbulent mixing. So different parts of the cloud that formed at different updraft velocities or different cloud bases are thoroughly mixed at higher points in the cloud. The next thing I wanted to look at was the effect of the organic hygroscopicity, where hygroscopicity is a composition-dependent degree to which particles will readily absorb water from the atmosphere. Now, we can separate specifically the organic hygroscopicity from the total hygroscopicity, where the total hygroscopicity is just the sum of the volume fraction of each chemical component times the hygroscopicity of each chemical component. So here I can separate it into just inorganics and organics and just change this value to see how sensitive our results are just to the organic hygroscopicity. To give you some numbers, sea salt is very hygroscopic, readily absorbs water. It's the easiest to form cloud droplets, sea salt, aerosols. However, organics are the opposite. They're on the low end of the spectra. And they have a range of hygroscopicity ranging from 0 to 0.3. So in my sensitivity study, I'm going to actually vary the organic hygroscopicity from 0 to 0.3. So here's a similar figure to what I showed on the other slide. Here again, here I have the organic hygroscopicity. This does not affect the liquid water content. However, in some cases, it affects the cloud droplet number concentration a lot. If you look at the gray line. However, in other cases, the black, green, and blue are not very sensitive. Just to put some numbers on it, changing the organic hygroscopicity from 0 to 0.3 causes a 10 to 17% increase in cloud droplet number concentration for the background and ambient cases. But for the plume cases, it's 35%, and just for the cargo ship plume, and 900% for the smoke generator. So if you remember the chemical composition, the smoke generator was completely organic. So that makes sense that it's more sensitive to the organics. But we did think the background cases would still be affected more because they were at least 40% organic. So it's not a negligible fraction. So I wanted to look at incorporating one other variable, and that was the aerosol concentration. So this figure here is actually showing an aerosol distribution, where in green that was a measured aerosol distribution. Now, cloud droplets, for aerosols to activate into cloud droplets, there's two things that are important. One is the chemical composition, and one is the size. So if they're all the same chemical composition, then all that matters is the size. So for example, at one specific chemical composition, we can have a critical diameter at this diameter, which is about 150 nanometer or microns, or sorry, 150 nanometers. So all particles above that size would form cloud droplet. Now, if we increase the hygroscopicity, this critical diameter would shift to a smaller diameter, and we would have, again, more droplets form because the critical diameter is smaller. So what I wanted to do was vary the concentration between these two critical diameters. So the way I did this was I varied the concentration below the critical diameter where the organic hygroscopicity is very low, so 0.01. So that could be my D1 critical diameter from the previous slide. And then I compared that to the organic hygroscopicity on the x-axis, and the contours show the cloud droplet number concentration. So you can see at very high concentrations, it's much more sensitive to the organic hygroscopicity. But when we decrease that concentration, it's not nearly as sensitive just because there aren't many aerosols in that size range to activate to form cloud droplets. Now this top case is a plume case, that's why more sensitive than this bottom case, which is a background case. Now this background case, it was measured at about 55 particles per cubic centimeter. So that's already very low compared to the plume case. Nearly as sensitive for the background case as it is plume case. Okay, so now I'm going to go into results of Chapter 2. Chapter 2 is titled The Top-Down and Bottom-Up Aerosol Cloud Closure Towards Understanding Sources of Uncertainty and Deriving Cloud Radiative Flux. The objectives of this study were to perform a top-down and bottom-up closure between satellite retrievals, airborne measurements, and simulations of cloud microphysical properties. I wanted to identify the effect of a decoupled boundary layer on comparisons of airborne measurements and simulations. And then finally, I wanted to account for cloud top entrainment to reduce differences in radiator forcing between observations and simulations. So in this campaign, we had UAVs taking the vertical profile measurements. So here on the y-axis, we have height. And here are the variables that we were able to measure with the UAVs. So we have temperature, relative humidity. Those are important for the model inputs. And now here we have cloud droplet extinction. So we don't have the cloud droplet concentration size. Instead, we have this other measurement, which is cloud droplet extinction, which I can derive from the cloud droplet number concentration and size simulated. So I can get a simulated cloud droplet extinction compared to this observed cloud droplet. And then finally, we have OPC concentration, which is the particle concentration of particles above 300 nanometers in size. And this parameter will be important for identifying the state of the boundary layer, which I'll talk about more in a few slides. So the first thing we did was look at the cases that we could form a hot closure. NASA Polar Orbiting Partnership satellite. The way we did this is what we extracted the effective radius from of the droplets from satellite measurements, and then we could convert this effective radius to a volumetric radius, which is similar to the volumetric diameter I talked about in the last chapter, and use an empirically derived linear relationship. We use an empirically derived linear relationship to convert to volumetric radius. So with that volumetric radius, we can derive the cloud droplet number concentration by dividing the adiabatic water content in the cloud by volumetric radius. Now when I do this, so here I have the satellite cloud droplet number concentration on the y-axis. And on the x-axis, I have the aerosol cloud parcel model cloud droplet number. And there's only a few points that we could do closure for, but they are within 30% of each other, which is the expected error for this satellite retrieval method. That was defined by one of our colleagues, Danny Rosenfeld. So next, I'm going to go through the bottom-up closure. So that's closure with the aerosol cloud parcel model and our measurements of cloud droplet extinction. So here in green, the dark green, we have our cloud sample. The gray is just cloud-free. And the light green is just a mixture, so it's not necessarily representative of the cloud. So what I'm going to do here is compare the dark green to the black line, which is my adiabatic simulation. And as you can see, they are different. Now, to give you some perspective, I've converted these both to shortwave radiator forcing of the simulated cloud versus the observed cloud. So I'm taking the radiator forcing of the parcel model, subtracting it by the radiator forcing that was observed to get a difference in radiator forcing. So here in this table, I show 5 cases that we looked into, looking at the difference in radiator forcing. And you can see that they have a big range, ranging from 11 to 88 watts per meter squared. And just to give you some perspective, the global daily average irradiance is 340 watts per meter squared. So, first thing I looked at was boundary layer decoupling, as that could affect our parcel model simulations. Now we found that a greater difference in cloud radiator forcing occurred in decoupled boundary layers. So what is a decoupled boundary layer? Well, typically in a coupled boundary layer, First, let me explain the axes. So on the y-axis, we have height. On the bottom x-axis, we have the OPC number concentration. Now, typically in a coupled boundary layer, the aerosol concentration is well mixed throughout the boundary layer, so it would be pretty constant, the concentration, all the way up to the boundary layer inversion, just below the free troposphere. However, in a decoupled boundary layer, there's actually a second stratified layer here, which prevents the mixing between these two layers. So there's actually a difference in the aerosols measured at the boundary layer than the aerosol measured here, which will actually enter the base of the cloud. And this is important because typically we have measurements at the ground, just because they're much cheaper than taking vertical profiles. And this well-mixed assumption for a coupled boundary layer is common and necessary because without it, then we can't be sure that our measurements are representative of what's forming our cloud. So, looking at the model results, we found that we will overestimate cloud radiator forcing in a decoupled boundary layer cloud. So these three cases on the left, different cloud radiator forcing difference than the two cases on the right, which were clouds in a decoupled layer. Next thing I wanted to look at was the cloud top entrainment. So here we have this diagram that I showed at the beginning. And I'm going to talk about a variable called the equivalent potential temperature. And what that is the temperature the air would be if you condensed all the water vapor out of it. So all the latent heat you would get from that process. So since it doesn't matter how much liquid water there is, it's actually conservative in the cloud. So if we take the equivalent, so we have the equivalent potential temperature throughout the cloud. And since it's conservative, we know that it's just a mixture of the air with an equivalent potential temperature at the cloud base and the air with an equivalent potential temperature that was entrained. So with that, we can use this equation to calculate the fraction of air that was entrained into the top of the cloud. So here's the same figure I showed before, but now in pink we have the adiabatic simulation with entrainment included. And as you can see, it's much better than the adiabatic simulation. And to show the numbers, this highlighted case on the left is this figure here on the right. The difference in radiator forcing decreased from 48 watts per meter squared to 20 watts per meter squared. And for another case that I didn't show, it decreased from 88 watts per meter squared to 33 watts per meter squared. Okay, so now we're going into chapter 3. This chapter is a little bit different. We're not using the parcel model, and we're going to talk about actually marine aerosol. So we talked about physical properties that affect, or physical processes that affect the clouds, and how pollution can affect the clouds. Now we're going to talk about just marine aerosols. What affects marine aerosols? Because in the absence of pollution over the ocean, the only thing that affects the clouds in terms of number, or the main thing that affects the clouds is the number of aerosol formed in the marine boundary layer. So this chapter is titled Higher Contributions of Marine Sulfate and Sea Spray to Cloud Condensation Nuclei in Late Spring than Late Autumn. The objectives of this study were to determine the marine sources of aerosol particles, identify how free tropospheric entrainment affects marine boundary layer aerosol properties, and we wanted to apportion the CCN based on particle sources. So I showed this figure at the beginning where we have 3 different marine derived particle types. One is the primary marine sea salt coming directly from the ocean as sea spray or from bubble bursting. The other two come from DMS, from phytoplankton production. One is a result of this DMS oxidation product condensing onto existing particles, and then the other is a result of the DMS oxidation products nucleating to form new particles. Now, condensing onto existing particles will change the particle properties, increasing its size and changing its chemical composition, where new particles forming, you just have more aerosols. Now, to do this, we needed to be able to measure the number of particles of each type. And the way we did this was we used a ETAMS, which stands for Event Trigger Aerosol Mass Spectrometer, that measures the single particle mass spectra. So with this mass spectra, we were able to cluster the mass spectra to get distinct particle types. From this, we derived 7 types, 4 of which were considered non-marine, so continental or polluted particles. We're not going to talk about those, but there are also the 3 marine types that I just discussed on the previous slide. So I'm actually going to compare 2 campaign measurements from 2 campaigns. One was conducted in November over the North Atlantic, and another in May to June in the North Atlantic. On this bottom x-axis, you can see cloud or condensation nuclei or aerosol concentration for particles greater than 180 nanometers. That was just a limitation of the measurement technique. And then we have the number fraction of each type, so going from 0 to 1. Now these measurements here are actually all the measurements, so it includes continental aerosol and pollution. So we wanted to remove those and we did that by correlating with continental tracers to get just the clean marine time periods. So you can see here, there's much fewer aerosol and much fewer of the non-marine particle types. And then we also needed to do one more thing, which is correct for sea salt. The ETAMS can't measure sea salt very well, simply because of how it works. It vaporizes the particles to measure its composition, and sea salt does not vaporize, so we only were able to measure a small fraction of the sea salt type. However, we do have filter measurements of the sea salt, so we were able to correct for this with that. And then finally, all of these were condensation nuclei of particles greater than 180 nanometers. So after that, we were able to apportion them to CCN. So just calculate how many of these particles are CCN. So here on this y-axis, we have the CCN concentration between the 2 campaigns. And one of the obvious things you can notice between the differences is the number concentration between November and May to June are very different. And a large part of that is because there is much more of these 2 sulfate types in May and June. The reason for that is because the peak in phytoplankton is in the phytoplankton productivity is actually in May to June, where the minimum is in November. So in May to June, we have more of the DMS that forms these 2 sulfate particle types. Now, you might be able to think, well, we can correlate these types with DMS concentration. And we tried, we did get a few weak correlations. Let me go over these axes. The top 2 plots are from the November campaign, showing the correlation from the particle type, where we have the added sulfate and the new sulfate type. We're comparing the DMS and seawater DMS. And on the bottom, it's the same thing, but for the May-June case. We also have this MSA measurement, which is one of the oxidation products of DMS. Now, there are a few where I fit these lines that have very weak correlations. So why is it that we only getting weak correlations sometimes and sometimes no correlation at all? Well, there are a few things that also affect the number concentration of each of these. One is the added sulfate type can be influenced by the number of existing particles. So this type is the particle type that forms from DMS products condensing onto existing particles. So if there's more existing particles, you might get more of the added sulfate type. Now the other type, the new sulfate type, is a little more complicated. It actually comes from the free troposphere. It's formed in the free troposphere. And the free troposphere is affected by long-range transport. So you might get these particles forming at one location, but then it could be affected hundreds of kilometers away. So here I'm going to show you some evidence of these particle type, the new sulfate type actually being entrained into the boundary layer. So here I have a vertical profile from an aircraft. On the x-axis, we have DMS, shown in red, and CN, or the condensation nuclei concentration, shown in blue. We do have two ship-based measurements to connect to our aircraft measurements. And then the last variable is temperature, shown in the top x-axis. Now the temperature is important just because we can find where the inversion is, where you can see it right here. And above this dotted line that I drew is going to be considered free troposphere, and below it is the marine boundary. So by looking at this plot, you can see in red that the DMS concentration does decrease in the free troposphere, but it's not zero. And we know it comes from the ocean. So it is mixed up into the free troposphere. If you look at the blue, which is the CN concentration, we have this peak here in the free troposphere, about ranging from just above the inversion all the way up to just over 1,500, or 1.5 kilometers. So we looked at the aerosol distribution, specifically from 1 kilometer to 1.5 kilometers. And we got this distribution here, where we have a peak in the number concentration at about 25 nanometers in diameter, which is very small and representative of newly formed particles. Now we looked at the distribution at the surface from the ship as well. We have the same mode, but it's actually a lot smaller in concentration, suggesting that it did originally come from the free troposphere, where it's higher in concentration. And then last, we looked at the composition of the particles that we measured, and they were mostly the added or new sulfate types, shown in these red and pink bars. We also have the just bulk AMS organic and sulfate concentration shown in the red and green, and the bulk mass concentration just shown in black. Now, the main reason that these new particle types form in the free troposphere, not in the boundary layer, is because there's a smaller total surface area for the DMS oxidation products to condense onto in the free troposphere. So if you look at this mode here, larger mode particle, this is going to account for a large part of the surface area, but we have a much higher amount of these particles here. So the total surface area of particles in the marine boundary layer is much greater than in the troposphere. And then the other thing that can affect it is temperature. So cooler temperatures are more likely to cause reflation of particles. So it's typically cooler in the free troposphere, so that's also another reason why. So we didn't always have those beautiful So I wanted to look at something we had a lot of, and that was balloon measurements, radiosondes. We had about 2 to 3 of those a day on the cruises. And they don't give too many variables, but one thing I couldn't do was look at the inversion strength. The idea being, if the inversion strength is really strong, then you'll have less entrainment of particles from the free troposphere across inversion. So what I did was I looked at the convective inhibition integrated over the inversion, where convective inhibition is just the amount of buoyant energy needed to overcome stratification. So in these plots here, we have sin, or convective inhibition, on the x-axis, and the particle type fraction on the y-axis. So if you look at the x-axis, we increase the, for increased conversion strength, we're going to have less entrainment, so we're going to have less of this new sulfate type. The added sulfate wasn't really correlated at all, suggesting that some of it might come from the free troposphere, but a lot of it also comes from forms in the boundary there. So now I'm going to just go through the conclusions of each chapter. In chapter 1, we talked about using a distribution of updrafts and cloud-based heights, and showed how that broadened the cloud droplet distributions. We also showed that the contribution of organic composition to droplet formation show small effects for all cases except for the ship and the cargo. The ship and the smoke, the generated smoke. In chapter 2, we saw that the cloud droplet concentration estimated from satellite-derived effective radius are within 30% of the aerosol cloud parcel model droplet concentrations. And then we found that ground-based measurements of aerosol in the marine boundary layer are not representative of aerosol in the decoupled layer that might actually lead to the formation of the cloud. And then we saw that accounting for the cloud top entrainment greatly reduces the difference in simulated and observationally derived radiative forcing. For the cases that I showed, it was by about 30 and 50 watts per meter squared. And then in the final chapter, I showed that contributions of sulfate to CCN varies seasonally due to the difference in DMS emissions. Sea salts account for most CCN in the fall because of the lack of marine sources, specifically the marine sulfate aerosol types. And finally, the formation of new particles is more likely to occur in the free troposphere and entrain into the marine boundary layer. And with that, I just want to acknowledge all the people that helped with my progress and helped me collect all the measurements throughout all the campaigns and guided me through my research. Couldn't have done it without all these people. Especially when I thank the Russell Group and the GMUE group in difference. That's it.
Great. Questions for Kevin?
Yeah, so the new sulfate particle types you're seeing at lower levels, do you think those are purely from entrainment from higher levels up, making their way down below, or that you have a progression of new particle formation starting at lower levels that continues to increase, and then or you have more at higher levels?
So no, what I'm showing is that they actually form in the free troposphere because there's just in the boundary layer there's just a lot more aerosols, so it's more likely that the DMS oxidation products will condense onto existing particles.
Towards that middle regime there.
Yeah, but in the free troposphere, there's just very little surface area, so the concentrations will build or the temperature will decrease enough where you'll actually have more likely. Now, we have seen this can also occur in the boundary layer, but it's very rare that the number concentration of particles are low enough and the temperature is low enough. So that's only under very specific circumstances in the boundary layer.
In the vertical DMS profile you showed, that's in the gas phase?
Yes,
Is
that's
that
in the
PTAMS?
No, that's from PTRMS, which I'm not too familiar with. That was a measurement from a colleague.
And CN is total particle counts? Or
Yeah,
just
the total particles are independent of size. You can see it's the peak here in the free troposphere.
You had one plot that you corrected your 88 plus or minus 8 went down to like 33, and you corrected another one of your clouds once you had it counted for, if it was the entrainment, but, what happened to the two that you didn't correct? Were they not affected by entrainment?
So those we didn't have evidence that they were affected by entrainment. What I looked at was the lapse rate, and if they had a sub-adiabatic lapse rate, it suggested there was some warming process, indicating either, most likely indicating cloud top entrainment because it was drier and warmer. We also saw that the liquid water, or the total water content in these clouds were decreased. Yeah.
Thanks, Kevin. You made a lot of progress in modeling warm clouds and observing, understanding them. I imagine this goes a long way towards making GCMs, climate models, better able to realistically reproduce the global radiation budget. Can you say a little bit more broadly about what is the state of the science and the big questions remaining in, being better able more realistically to model the global radiation budget, that's associated with clouds, including cold clouds and, what's involved in like freezing nuclei like measurements.
I'm not too familiar with freezing nuclei, but in terms of warm clouds, you can't do nearly as detailed models with a global climate model because it would just take forever. So what we have to do is just take many measurements. As you can see here, I have 5 cases. That was over a month. It's very difficult to get just a few cases, but that's not really enough points to get good statistics. This is all at one location, so we really need more measurements throughout the globe. And as you can see, this makes a fairly big difference. Just this entrainment, which I had in 2 out of the 5 cases. So again, that's 5 cases, not enough for statistics, but if I was forced to, 2 out of 5 is not negligible amounts. So the whole idea with all the things I showed today is we need more measurements to be able to compare with our GCMs and to better parameterize our GCMs. And if we need to, or if it's possible, to do empirical relationships with observations to make it easier for our GCMs to model what we're observing. Is that all of your questions?
Thanks.
Okay.
Any other questions? Where was your plant? Yeah, wasn't June gonna ask a plant question?
No, don't worry about it.
Okay, well, then with that, let's give Kevin a hand.